So I'm going to look at ARMA processes and their connection to Hankel matrices through their covariances. So to put this in perspective, let me start with the Whiteson stationary stochastic process. That means it's an autocorrelation function which is R of T1 comma T2, which is expected value of x of T1, x of T2 star, is a function of the difference of the time indices. In other words, this is a function of, let's say, T2 minus T1 or T1 minus T2. So I'm going to write it like this. So in general, I'm going to write this as RT2 minus T1. Now, if I discretize this, I look at time indices T1, T2, etc., and I define y to be ak, let's say x of ai, x of ti, and then expected value of y squared is, of course, expected value of y star. So that will be double summation ij, ai, aj star. Here we have expected value of xti, xtj star. Let's say I put ti as it. In other words, I'm uniformly sampling this as jt. So this will become a function of j minus I multiplied by capital T. So I'm going to denote this whole quantity as r j minus I. Instead of what I'm writing is r of j minus I multiplied by capital T, but I'm going to use this notation. So notice that, so this is like the mean squared power. So if I over these, let's say I'm going to do I equal to 1 through n, some finite number of samples. So here also I equal to 1 through n, j equal to 1 through n. So this power, we can write this as double summation ai, aj, rj minus I. So if you use a little bit of matrix algebra, this you can write it as I equal to 1 through n, j equal to 1 through n. We can write this as A transpose TA. That's the whole point. Where A is, so in other words, you can write it like this. So this is A1, A2, etc., An. This is our vector A. And this is its transpose, so this is A transpose here. So that will be A1 star, A2 star, etc., An star. And these are the covariants. So this has a nice form. This will be R0, R1, R2. If you just expand it out, Rn minus 1. So I'm going to call so this has the toplets form. So this will be R1 star, R0, R1, etc., Rn minus 2, and the last one is Rn minus 1 star, etc., R1 star, R0. So this is the toplets matrix of size n by n using the autocorrelations R0, R1, R2, etc., Rn. So what this means is, of course, the power is non-negative. That means for any stochastic process, a stationary stochastic process, this quadratic product is non-negative. This is the same as saying that from a little bit matrix algebra, all these TNs, the toplets matrices generated from the covariance matrices are always non-negative definite. So that's where we are starting. This is true for any autocorrelation function. I mean, this is n by n, so if I write it as up to n, this will be Rn star, Rn minus 1 star, etc., R1 star, R0. So the diagonal entries are all R0s. So this is according to our notation Tn. So all the toplets matrices for has this positive or non-negative definite properties. This is true for any process. Now, what we mean by an ARMA system is the process is driven by, so one representation is this way. You have a discrete process, a discrete white noise process driving a rational system generating an output process. So if this is a rational system, in other words, the ratio of two polynomials, if h of z is of the form bc over az, then you have where bc is b naught plus b1z plus etc. bq over 1 plus a1z etc. apz. So let's say we start with a rational system. Wn is a white noise process. So you have the input-output relation x of z over w of z is h of z, or x of z is h of z multiplied by w of z, it's a z transform. And then if you cross multiply and rearrange the terms, you get this expression. And so this is what we mean by an autoregressive, because if you if you look at here, the output process is averaged or regressed over itself over p terms, and there is a moving average term. In other words, this is like a summation or like an averaging of the process, because you can think of this as generalized weights rather than equal weights. You have b0, b1, etc., bq. And so this is the moving average piece, and this is the autoregressive piece. And using q terms, and this is using p terms. So essentially this is such a process is written usually like this, ARMA pq. Now, the thing I want to show is some relation between the covariances of such a process, but rather than, so this is a Toeplitz matrix, because all these diagonals are the same. But of course, this is true for ARMA processes also. But for ARMA processes being this special, you can actually develop some additional conditions, which is what I want to go into. So to start with, if I expand this as a power series and write this as sigma hk zk, k equal to 0 through infinity as a, in other words, remember there are, another way to see this is that this is a polynomial of degree q in the numerator, a polynomial of degree p in the denominator. So a polynomial p has p factors, p. So these represent the poles z minus z1, z minus z2, etc. If you want to write it like this. And similarly, the numerator can be written as also, so they represent the zeros. So these are the p poles and the q zeros. And so you can do partial fraction or whatever, and you can come up with a power series expand. Now if you cross multiply the denominator with this, you can equate the numerator. You can begin to see that, for example, if you cross multiply, you will see that h naught is equal to b naught. So you will get these terms, b naught equal to h naught, then b1 equal to h naught a1 plus h1 by comparing the b1, comparing the coefficient of z. So on the other side, because this is going to be h naught plus h1z plus h2z squared plus etc. plus h and z, and it goes on. Right? So the corresponding z term will be from here. You can see it will be h1 plus h naught a1, so which is what I have written, h naught a1. So we can do this up to bq. Bq will be h naught aq plus h1 aq minus 1 plus etc. Up to hq. And of course, on the right side, if you cross multiply, there are other higher degrees are there, but on the left side, the whole thing stops at q. So we will get additional relations equal to 0. So if you keep doing this in general, we will get h naught aq plus I plus h1 aq plus I minus 1 plus etc. Equal to plus hq plus I. So you will get an infinite number of equations for all the other terms. So if you let I equal to we can start by doing I equal to P minus Q, then P minus Q minus plus 1, etc. Then we are going to get the following equation. So when you put I equal to P minus Q, you will get here AP. So you get 0 equal to H naught AP plus H1, or I'm going to put the 0 on the other side. H1 AP minus 1 plus etc. HP minus 1 A1 plus A naught plus HP equal to 0. And if you put the next one, it's so if you put I equal to P minus Q plus 1, this is going to be P plus 1, but AP plus 1 is 0, and this will be H1 AP, etc. So the next one is going to be H1 AP plus etc. H2 AP minus 1 plus etc. So in general, so if you the next equation etc., this will be HP AP plus HP plus 1 AP minus 1 plus etc. H of 2P minus 1 A1 plus H2P equal to 0, and so on. So notice here, you can see, if you this you can write as a matrix multiplied by a vector equal to 0. The vector is AP minus 1 etc. A1 1. That vector is certainly not 0. That means that coefficient matrix must have determinant must be 0. But that coefficient, if you arrange, you will get so you will get this matrix H naught, H1, H2, etc., HP. Then next one H1, H2, H3, etc., HP plus 1, etc., HP plus 1, etc., H2P. So this is Hankel matrix because these entries are all equal. So I'm going to call this HP, but this rank should be 0. I'm sorry, the determinant of this must be 0, because this multiplied by the A vector is all 0 vector and the A vector is non-zero. And you can clearly see, but if you put AP plus 1 etc. equal to 0, you will see that if you even if you generalize this to Hn, where this is n, and if you define this to be Hn, then we get the result that determinant of Hn equal to equal to 0 for n greater than or equal to p. I believe this result for rational systems is due to Kronecker, I think. In any case, you can see because there is only so much freedom here. You have p parameters here, q plus 1 parameters here. So in total, p plus q plus 1 parameters. So this is actually a necessary and sufficient condition. If a system is ARMA, then all the Hankel matrices generated from the impulse, in electrical engineering, these are the impulse response coefficients. These coefficients have a property that the Hankel matrix generated from them will be of certain rank. In other words, the easier way to say that the determinant of these Hankel matrices is 0 beyond a certain stage. So that stage is going to give you actually the degree of the denominator. So maybe singular values or something, you find out where this condition starts, that will give you the value of p. Knowing p, you can go and determine the q's also, because you can exploit the additional relations. So in general, you could say that if a system is ARMA, then for sufficiently large n, the determinant of all the Hankel matrices generated from this impulse response is 0 for n large enough, in a particular n greater than or equal to p. So how do you connect this with the covariances? If the process happens to be if the system is being driven by, let's say, Whiteson stationary white noise, so that this is also Whiteson stationary, that means it has got its autocorrelation functions. And I want to show that the autocorrelation functions actually has a similar property. So the noise being, remember, this is the input to driving noise. So the noise has the property that expected value of Wn multiplied by, so the noise are uncorrelated. So this means this is the current value of the noise is uncorrelated with the previous values, and you also have expected value of Wn x of, this is also 0. What this means is, if you look here, xn only depends on the previous values of xn and the current and the previous values of w. So so the previous values of xn does not depend on the future values of wn. So wn is also uncorrelated with xn minus k. So from here, if I look at Ri, which is expected value of xn, x of n minus I star, and then if I substitute for xn from here, I bring this xn and substitute it here, this will become minus summation ak from here. So this is xn, so that's going to be x n minus k n minus I star from here plus summation bk, you have w n minus k, then xn minus I star. There is two expected values, expected value here and expected value here. So this term is I minus k. This term is R of I minus k because by definition, somewhere we have defined, right? So this is the second, and this will be whatever it is. But you can see that if n minus k is beyond this, then these values will be 0. First of all, here k goes from, in this case, here k goes from 1 through p, and here k goes from 0 through q. So the worst value of this is q, n minus k. And if you notice here, here you have n minus k. So if I take the difference, which is this minus this, which will be this, my I minus q has to be greater than or equal to 1. So that this my right, so this minus this, so that will be I minus q greater than or equal to 1. So that means I minus q greater than or equal to 1. This will be 0 from here because this minus this is k greater than 1, this is 0. So this minus this is I minus the worst value, which is I minus q. So this is the same as saying that if I is greater than or equal to q plus 1, these terms will not be there. So you have a relation between the covariances. So the relation is so I'm going to bring everything to one side. So this is going to look like ak or I minus k plus ri, I equal to 1 through, I'm sorry, k equal to 1 through p. So we can also include k equal to 0. This is equal to 0 for sufficiently large I greater than or equal to q plus 1. If q is unknown, you know, if I is large enough, then this relation is true. So the whole point is, if you arrange this again in a matrix form, it is going to look like this, except that the H will be replaced by the R case. So to summarize, that relation says if I define again, once again, Hn using R0, R1, R2, etc., Rn, so notice that if n is large, you get Rn plus A1 Rn minus 1. So you have, and the last term is going to be here, AP Rn minus P. So a vector equal to 0, since this vector being non-zero, you will get that this determinant has to be singular, which is the same as once again for n large enough, the autocorrelations also satisfy this property. So if n is large enough, then if the system is, or the output process is ARMA, the autocorrelations always, of course, the Toeplitz matrices are non-negative, but the Hankel matrices have rank structure. So the easiest way to say is that the best way to say is that this Hankel matrices, large Hankel matrices will be singular. So as you keep, so at some stage, rank is it is going to have some rank, and that's going to give you the P. And beyond that stage, the Hankel matrices will be all singular.